In this video, I'll show you how to use derivatives to maximize an area. Here are the main points to be addressed in the video. When trying to maximize or minimize a value given a situation, you should first determine an equation for the value you're trying to maximize or minimize. Once you have the equation to maximize or minimize, you should differentiate and determine locations where the derivative is either equal to 0 or undefined. Consider the places where the derivative is 0 or undefined along with the endpoints of the domain, if they're introduced by the situation, to determine global maximum or minimum. A farmer wants to start raising goats. So the farmer decides to build a small rectangular pen next to the barn. Here's a picture of what the farmer would like to make. And I'll point out the barn is used for one side of the pen. There's only 300 feet of fencing material. The goal is to find the dimension of the pen that will produce the largest area with the limited amount of fence. Let's take a look at this situation from the above. Let's build an example of a pen. In this drawing, the pen has dimension of 280 feet by 10 feet. However, there are lots of other dimensions that use 300 feet of fencing material. For example, it might have dimension of 250 feet by 25 feet, or it might have dimension of 200 feet by 50 feet, or 100 feet by 100 feet, or it might be really tall and narrow and have dimensions of 10 feet by 145 feet. And since it could have any of these dimensions, we can use variables to represent the quantities. We'll use L to represent the length of the pen, and W to represent the width of the pen, and A to represent the area of the pen. And these variables could take any values as long as the length and the width add to 300 feet. There are infinitely many options for length and width, and we need to find the values that maximize the area. We'll do this by creating an algebraic model for the area of the pen. Let's try to write down a formula for what we're trying to maximize and a formula for the constraint. We're trying to maximize the area of the pen, which is the length times the width. We're constrained by the amount of fencing materials. We have 300 feet, which is the perimeter of the pen, L plus 2W. Now, we have two equations and two variables. We'd like to have everything in terms of a single variable. So what can we do next? The general strategy is to try to write one variable in terms of one another. For example, we could take our constraint equation and rearrange it. So now L equals to 300 minus 2W. Once we've done this, we can take our equation for area and substitute our new expression of 300 minus 2W for L. Then we can distribute W to get the area is equal to 300W minus 2W squared. Now, A is a continuous function of a single variable, W. The smallest value W could be is 0 because we can't have width of a pen be negative. The largest value W is 150 because if the width was 150, then all 300 feet of fencing will go into the width. So the domain of A is all numbers between 0 and 150. Next, to find the value of W that would maximize the area of the function in the domain, we need to find the critical points of the function and also check the endpoints. To do this, we first compute the derivative of A with respect to W using the power rule to get A prime equals 300 minus 4W. Critical points are where the derivative is 0 or undefined. Since a prime is a linear function, it is defined everywhere. To find where is equal to 0, we set a prime equal to 0 and then solve for w to get w equals 75 as a critical point. To figure out the corresponding length, we can use our 300 minus 2w equation to get the length of 150 feet. Next, we should check the endpoints. One endpoint has w equal to 0 feet, which would correspond to the length of 300 feet. The other endpoint is when w equals 150 feet, which corresponds to the length of 0 feet. Which of these values for the width would give us the largest area? If we use a width of 0 feet, we would have an area of 0. Similarly, if we use a width of 150 feet, the length will be 0. So we also have an area of 0 feet. If we use the width of 75 feet, we will get an area of 11,250 square feet, since the endpoints and critical points represent the only possible place for A to obtain maximum or minimum values. The maximum possible area for our pen must be 11,250 square feet, and this happens when the width of the pen is 75 feet and the length of the pen is 150 feet. So, our general strategy was to make an algebraic model for the quantity that we wanted to maximize. Then, we wrote an expression for the constraint and used this to write one variable in terms of one another. This let us rewrite our model in terms of single variable. We identified the domain and found the critical points and endpoints. We computed the area for each of these values of w to find the value that produced the largest area.